Hello everyone, this is Rita, Assistant Professor of Physics from Government College for Women Bodia Kheda, Fatehabad. In this video, I am going to discuss about polarization. I will discuss the topics Brewster law, law of Malus and double refraction. So first of all, I will talk about the term polarization, what this term is. As we all know that the electromagnetic waves have the transverse nature as well as the longitudinal nature. So we can say that the various phenomena are there which could be performed with light, like interference, diffraction, but they could not distinguish between the transverse and the longitudinal waves. So we need a phenomena which could transfer between two. So the polarization is that phenomena which could differentiate between the transverse and the longitudinal waves. A polarizing filter blocks out all the waves except those with vibrating moving with particle moving in a certain direction. So polarization works only for the transverse waves, not for the longitudinal waves. You can see here I have used a polarizer, and when we incident the randomly polarized set of waves on it, we will get as the vertically polarized waves which are parallel to the plane of polarizer. So we can say that what is polarization? Polarization is basically the characteristic of all the transverse waves, and it is the phenomena of restraining the vibrations of a wave in a particular direction. As the oscillations which take place in the transverse waves, they are in the different directions. So a transverse wave is unpolarized light. In an unpolarized transverse wave, the oscillations may take place in any direction at right angle to the direction of propagation. You can see here I have shown the direction of propagation as by blue arrow, and I have shown the various directions of vibrations in the unpolarized light by the red arrows. Now if we restrict the vibration in one direction, then we will say that the light is plane polarized. Now here we can represent the natural light. You can see here that I have represented the natural light with the red colored arrows. You know that the electromagnetic wave consists of vibrating electric field and the vibrating magnetic field. Both are perpendicular to each other and also perpendicular to the direction of propagation of the wave. Now it is well known from the experimental evidences that if we talk about the optical effects of light, then they all are produced by the electric vector E of the light wave. So whenever we talk about any phenomena produced by the light, we talk about the vibrations of the electric field E. So in generally we can say that the ordinary beam which is coming from sun or from the sodium lamp, it is unpolarized, means its electric vector keeps on changing in different directions in a random manner. If such a beam is incident on a polarite, the emergent light is linearly polarized with its electric vector oscillating in a particular direction. Now the direction of electric vector of the emergent beam will definitely depend upon the orientation of the polarite. If we get the vibrations parallel to the plane, then we can represent them by arrow, and if we get the vibrations perpendicular to the plane, we can represent them by the dots. So in natural light, we can say that the millions of transverse wave vibrations occur in all the directions perpendicular to the direction of propagation of wave. But for convenience, we take only the two rectangular components of vibrations, one component lying in the plane of diagram and the other perpendicular to the plane of the diagram. So whenever we talk in experiments or in our topics, for the unpolarized light, we will talk about the two rectangular components. One will be shown by the arrows and one will be represented by the dots. So this will be the representation of the natural light. Here the representation of the linearly polarized light. As you know that the linearly polarized light will be having the oscillations only in a particular direction. So when it oscillates at one angle, then it will be linearly polarized, and when the oscillations are in all the directions randomly, then it will be omnidirectional, means it is unpolarized, as you can see in the figure also. Now here I have shown that how we can produce the plane polarized light and how we can analyze it. You can see here that I have used here two polarizers, polarizer 1 and polarizer 2. In the first figure, you can see that the polarizer 1 and polarizer 2 having their planes perpendicular to each other. If I incident the unpolarized light, which is having vibrations in all the directions on polarizer 1, then after passing through the polarizer 1, we will get the polarized light. This polarized light will have the vibrations parallel to the plane of polarizer 1. Now if we incident this polarized light on polarizer 2, since you can see that the plane of polarizer 2 and this polarized light are perpendicular to each other, so it will not pass through polarizer 2 and we will get no light here. Okay, but if we keep on changing or keep on rotating the polarizer 2 such that the angle between polarizer 1 and between the planes of polarizer 1 and polarizer 2 will become less than 90, then slowly we will get the polarized light on the another side, but it will be of reduced intensity obviously. And when the plane of polarizer 1 and polarizer 2 will become parallel to each other, means when phi will become equals to 0 degree, then we will get the maximum intensity on the another side. So for getting the maximum intensity, the planes of polarizer 1 and polarizer 2 should be parallel to each other, and for getting the minimum intensity, they should be perpendicular to each other as shown in the first part. This is the mechanical experiment to show the polarization I have just talked about. If I use the pair of polarizers, first polarizing filter, second polarizing filter, then if I put them in this position as shown in this figure, then we will get the polarized light with the reduced intensity. In order to get the maximum intensity, we need to keep polarizing filter 1 and polarizing filter 2 with their planes parallel to each other. And for getting the minimum intensity, we should keep them in such a way that their planes are perpendicular to each other. Okay. Now here are the types of polarization. There are three types of polarization we will talk about: the linear polarization, circular polarization, and elliptical polarization. We will definitely discuss about all this in detail in the coming topics. So you can just see here the presentation of unpolarized light by the arrows, circularly polarized light, and the linearly polarized light. You can see here the arrow and dot, red dot. This dot is representing the out of page, and this black arrows, these are representing in the page. Now we will discuss about the various methods of production of polarization, that how we can produce the polarized light. There are various methods. We can produce by reflection, by refraction, by scattering also. We will discuss these topics in detail one by one, but before doing that, I am going to talk about some terms which we must know before starting. That is, the first one is plane of vibration. A plane which is including the direction of light propagation and the direction of electric field is known as the plane of vibration. You can see here in the figure that I have shown a tourmaline crystal whose plane of vibration is represented by AB, and its plane of vibration you can see here is represented by A, B, C, D. The vibrations in this plane will be known as the this plane will be known as the plane of vibration, and the plane represented here by dots, that is E, F, G, H, is representing the plane of polarization. These two planes will be perpendicular to each other. So the plane perpendicular to plane of vibration is known as plane of polarization. Now we will talk about the polarization by reflection. This method also explains the Brewster's law, well-known Brewster's law. This is a very important topic. Now what is this polarization by reflection? Now this phenomena was discovered by Louis Malus in 1808. What he has investigated, he showed that when a beam of ordinary light is reflected from the surface of a transparent medium such as glass or water, the reflected light is partially polarized, and the degree of polarization will depend upon the angle of incidence. At a certain angle of incidence IP, the light which is reflected is almost completely plane polarized. This angle of incidence IP will be known as the angle of polarization, or simply the polarizing angle of the medium. This angle IP will depend upon the nature of the medium, which means the refractive index, and also changes slightly with the wavelength of light used. For example, for glass, the angle of polarization is 57.5 degrees. You know that here I have shown you the blue colored light incident, which is unpolarized, having the vibrations in the two directions, and we get this red light which is reflected. It is completely polarized when the light incident at angle IP, that is at the angle of polarization. You can see in the figure also the angle between the reflected and the refracted beam is 90 degrees. This is also the condition for the Brewster law, which we obtain from Brewster law basically. So the Brewster law relates refractive index and the polarizing angle as mu is equal to tangent of IP. This relation is known as Brewster law, and this angle IP is known as the polarizing angle. We know that the refractive index of the medium depends upon the wavelength of light. So in that case, the polarizing angle will also vary with the wavelength of light. So the polarization can be completed for one particular wavelength at a time. Hence the complete polarization is possible with monochromatic light and not with white light, since white light consists of various wavelengths. So now we will discuss about the relation between IP and R. We know by Snell's law, mu is equals to tangent of IP. We know from Brewster law, we know that mu is equal to tangent of IP, and by Snell's law, we know that mu is equal to sine of IP upon sine of RP. If we equate those two relations, we will obtain the relation between RP and IP as RP plus IP is equals to 90 degree. So we can say that at the polarizing angle, the refracted and the reflected rays are perpendicular to each other. I have also told you about this condition in the previous figure also. Here you can see that the angle between the reflected and the refracted ray is 90 degrees. So we have proved that for this polarizing angle IP, we will get this condition. So this was the method by which we can produce the polarized light with the help of reflection. Now here is the another method, that is by the refraction we can also produce the polarized light. You know that according to Brewster law, when a beam of light is incident on the surface of a transparent medium, then the part of it is reflected and the rest part is refracted into the medium. The reflected light is partially plane polarized for all angle of incidence. But when the angle of incidence becomes equals to IP, means angle of polarization, then the reflected light is completely plane polarized in the plane of incidence. That is having vibrations perpendicular to the plane of incidence, which we have shown with the red dots in the previous figure. And the transmitted light on the another side is never completely plane polarized, because it contains the vibrations in the plane of the paper as well as in the perpendicular to the plane of the paper. And the intensity of reflected beam also is very weak, means we are getting two beams, a reflected beam whose intensity is very weak, and the another is the transmitted light which is not plane polarized. So in order to increase the intensity of the plane polarized reflected beam, what we should do, we should increase the number of reflections, and consequently we should increase the number of plates, right? So what we do, the light is incident at the polarizing angle on the first plate of thin parallel faced plates, one on the top of other, as I have shown here in the figure. If I use the piles of plates which are separated by the thin sheets of the papers with a central aperture, otherwise the plates will make good contact with each other and they will practically act as a single slab. So we should use a thin sheet of paper between them, we should separate them, right? So what will happen, that at each reflection the more of the component will get the vibrations perpendicular to the plane of incidence. They will be filtered out, with the result that the transmitted light will become richer and richer in plane polarized light having the vibrations in the plane of incidence. So nearly 10 plates, they are sufficient to get the completely plane polarized transmitted beam. So piles of plates can be used to increase the intensity of the reflected plane polarized and to produce the transmitted beam of polarized light. Okay. as you know that we have just filtered out the perpendicular components, so transmitted ray will consist only the parallel components, right? So we will get almost plane polarized light as I have shown in the figure also. Now the another method is polarization by scattering. When a beam of white light passes through a medium consisting of small particles of about the same size as the wavelength of light, then the light seen in the direction perpendicular to the incident beam will appear bluish. This phenomena is called as scattering of light, and the particles which cause the scattering, they are known as scatterer. In fact, we can say that the scattering of light occurs due to absorption and re-radiation of light energy by the scatterers. When the photons constituting the light energy fall on the atoms of the absorber, it gets excited and emits the light energy. Right. So we can say that polarization can also occur when the light is scattered. When the light strikes the atoms of the material, the electrons set into vibration. The vibrating electrons will produce the new electromagnetic waves radiated in all the possible directions. Now the newly generated waves will strike the neighboring atoms and they will continue the process. So we can say this scattered light is basically because of absorption and re-emission. So when the light is incident on the small objects such as particles of dust or smoke or air molecules, then it is scattered in all the directions. Now suppose that a beam of unpolarized light is incident on the scatterer along the z-axis. Since the light waves are transverse in nature, so all the possible directions of vibrations in the unpolarized light are confined to xy plane, obviously, means perpendicular to z direction. If we look along the x-axis, then due to transverse nature of light, the vibrations must be perpendicular to x-axis. Similarly, if we look along the y-axis, then we find that the light scattered in the direction perpendicular to the incident light is always plane polarized, and in all other directions it is partially plane polarized. So here you can see in the figure also I am getting the linearly polarized light in the two perpendicular directions, x direction and the y direction, and this z direction is representing, which is horizontal representation, so that is representing the z direction, that is the direction of propagation of unpolarized light. So this was the method of scattering with which we can produce the polarized light. Now here is an important law which is known as the Malus law, and it is a very important topic from exam point of view also. So what is this law basically? When a beam of light which is polarized by reflection at one plane surface is allowed to fall on the second plane surface at the polarizing angle, the intensity of the twice reflected beam, since we are using here the two surfaces, so the intensity of twice reflected beam varies with the angle between the planes of two surfaces. It has been found that when these two planes are parallel, then the intensity of the twice reflected beam is maximum. And when these two planes are perpendicular to each other, the intensity of twice reflected beam is 0. Right. So this was experimentally shown by Malus, and he used a completely plane polarized light beam and incident it on an analyzer. He observed that the intensity of the polarized light transmitted through the analyzer varies as the square of the cosine of angle between the planes of transmission of analyzer and polarizer. Here P is polarizer and A is analyzer, means the intensity which is coming out of the analyzer means I, it is directly proportional to the square of cosine of angle between the planes of transmission of P and A. Here I have shown here the angle theta, which is between the plane. The plane of transmission of P is represented by the green arrow, and the plane of transmission of A is represented by dots. You can see here the direction, and the angle between these two is represented by theta. So this was the definition of Malus law, that is I is directly proportional to cos square theta, right? So this law is known as the law of Malus. And let us consider that A here is representing the amplitude of the vibrations transmitted or reflected beam by the polarizer, and theta is the angle between the plane of transmission of P and A. Now we can resolve this A in two components, two rectangular components. The first component A cos theta is the parallel to the plane of transmission of analyzer. You can see here that the plane of transmission of A and this component A cos theta, they are parallel to each other. The second component A sin theta, it is perpendicular to the plane of transmission of the analyzer. So you can see that only the component A cos theta will pass out through A and A sin theta will be blocked by this analyzer. So we will get the final intensity which is coming out of the analyzer is I, which is directly proportional to A cos theta square, since intensity is directly proportional to square of amplitude, and here the amplitude is A cos theta. By just omitting the proportionality sign, we will just put here K as the constant of proportionality. So we will get I is equals to Ka square cos square theta. If I replace Ka square as I0, then I can say I is equal to I naught cos square theta. So this is an important relation and it will give the law of Malus. So we can also say that here I naught is equal to Ka square is the intensity of the incident plane polarized light, and K is the constant of proportionality. This is of course 1/2 of the intensity of the unpolarized light striking the polarizer. Okay, so we will talk about some special cases here, that if the polarizer and analyzer are parallel to each other, that is if theta is equals to 0 or 180 degree, then your I is equal to I0. It means that when P and A are parallel to each other, the intensity of light transmitted by the analyzer is equal to that incident on it. Means we will get the maximum intensity. And second case is if the polarizer and analyzer are perpendicular to each other, that is theta is 90 degree, then intensity coming out to be 0. And the third case here is that when the unpolarized light is incident on the analyzer, the intensity of the transmitted light is 1/2 of the intensity of the incident light, since the average value of cos square theta is 1/2. So this is the Malus law and it is a very important law. Now the next topic I'm going to start here is the double refraction. Now what is the meaning of double refraction? We have talked about the refraction in the lower classes, just term refraction. What was that? When the light is incident on a medium which is isotropic in nature. Isotropic means which is having the same properties in all the direction. Then the refraction takes place. When then the refraction which takes place, it will obey Snell's law. And the refraction will take place only in the one direction. That we have talked in the lower classes. This topic we have studied in the lower classes. But if we use a crystal such as calcite, which is anisotropic, means which is having the different properties in the different directions, then in this case, if a ray of ordinary unpolarized light is incident on such an isotropic crystal, then it will split up into two refracted rays in place of one. So the crystal having this type of property are said to be doubly refracting, and this phenomena is known as double refraction. Some crystals which are having these nature of doubly refracting, they are mica, sugar, topaz, you can use them. Okay, so this term double reflection means birefraction. So when the light is refracted in two such rays, such that vibrations direction oriented at right angle to each other, then the traveling at the different velocities, this phenomena is termed as the double or the birefraction. So I have shown here the phenomena of double refraction. You can also represent it by putting a black dot on the sheet of paper and view it through a calcite crystal. Calcite crystal is an anisotropic crystal, means a doubly refracting crystal. What you will see the two images of the dot are seen as here shown by the picture B. Then on rotating the crystal about incident ray as axis, one of the two images will remain stationary that is known as the ordinary image. Here I have represented by O. The second image rotates around the first and it is called as the extraordinary image. Here I have represented by E. So we will get the two images in this case. Okay. So we can say that how the polarization by double refraction could be produced. The phenomena in which the ray of light incident on a calcite crystal or a quartz crystal is split into two refracted rays is called the double refraction. One ray obeys ordinary laws of refraction. Sin I by sin R is always constant for all the values of angle of incident. This is known as ordinary ray. And the second refracted ray which does not obey the ordinary laws of refraction, then that is called as the extraordinary ray. Now I will talk about this as I have here shown you the phase of the calcite crystal. Since the two opposite phases of the calcite crystal are always parallel to each other, so the two refracted rays, that is ordinary and extraordinary, will emerge parallel to the incident beam. But they will be displaced by a distance proportional to the thickness of the crystal. As you can see here also they are displaced by some distance. For the normal incidence, the ordinary ray will pass out straight to the crystal, whereas the extraordinary ray will be refracted at some angle and will come out to the parallel of the to displace from the incident ray. Now how does the polarization of rays will take place? Both the ordinary and extraordinary rays are obtained by the double refraction. They are plane polarized in perpendicular planes. The vibrations of ordinary ray being normal to the plane of paper and that of extraordinary ray will take place in the plane of the paper. As I have shown here, the vibrations of ordinary ray by dots and the vibrations of extraordinary ray by the arrows. So you can say that the ray which obeys the Snell's law of refraction is known as ordinary ray, and the another ray which does not obey Snell's law is known as the extraordinary ray. Also one important point here I want to discuss is that the refractive index for ordinary ray is known as the ordinary refractive index and its value is constant. Its value for calcite is generally 1.658 and refractive index for extraordinary ray is represented by mu E and its value is not constant but its value varies between 1.48 to 1.65. And since we know that the refractive index is inversely proportional to the velocity of light in the medium. So clearly, since the refractive index of ordinary ray is fixed, so the velocity of ordinary light in a crystal is same in all the directions. But the velocity of extraordinary ray will be different in the different directions. Now we will discuss some points about the calcite crystal. As I have already told you that the calcite crystal is an anisotropic crystal, means having the properties in all the different properties in the different directions. This is also known as Iceland spar calcium carbonate crystal. It is a colorless crystal which is transparent to visible and to ultraviolet light. Okay. So generally in nature it occurs in different forms and out of which it break up into simple rhombohedron form as I have shown here, in which it is having the 6 phases. Each of the 6 phases of the crystal is a parallelogram whose angles are 78 degree and 102 degree nearly. At the two diametrically opposite corners, here I have shown the diametrically opposite corners as A and B in the first figure. In the upper figure you can see the two diametrically opposite corners A and B. You can see here that the 3 angles of the faces meeting, they are obtuse. You can see here at the A, the 3 angles which are meeting, they are of 102 degree. All the 3 angles are obtuse angles. So this corner will be known as the blunt corner, the very first term. The A and B will be known as the blunt corner. Except A and B, at all the remaining 6 corners, the angles, one of the angle will be obtuse and other 2 angles will be acute. You can see in the picture at the other corner we have one angle as 102 which is obtuse and the 2 angles as 78 degree which are acute. Right. Now the next term, optic axis. the line which is passing through any one of the blunt corner, that is whether it is passing through A or it is passing through B, then and equally inclined to three edges meeting there, it represents the direction of the optic axis, as here I have shown it by the red colored line. This is the optic axis. So optic axis is a direction and it is not a line. No separation of a ray into ordinary and extraordinary will occur in this particular direction. It means if the ray passes along the optic axis through a crystal, then the velocity of ordinary and extraordinary ray along this axis, along this optic axis, will be same. So the optic axis is the particular direction through the crystal along which there is no double refraction. Crystal is symmetrical about this axis. So optic axis is also known as crystallographic axis. Now the next term is the principal section. The plane containing the optic axis and the perpendicular to the pair of opposite phases of the crystal is known as the principal section of the crystal for that pair of phases. In this figure I have shown here in the lower picture, part A is representing the principal section of the calcite crystal. The principal section always cuts the surfaces of calcite crystal in a parallelogram having the angles 71 degree and 109 degree. So an end view of the principal section perpendicular to the pair of opposite phases of the crystal cuts these phases in a line parallel to the shorter diagonal of the phases. Here I have also represented the phase of the crystal in the figure B. You can see here also. So it is found that the ordinary ray is polarized in the principal plane and hence its displacements are shown by dots. The extraordinary ray is polarized perpendicular to the principal plane and its vibrations are shown by the arrows. So in this manner, the plane polarized light can be obtained by the double refraction. Here I have used the two terms lower in this part also, that is uniaxial crystal and biaxial crystal. So what are these crystals? Basically, the uniaxial crystals are like quartz, tourmaline, nitrate of soda, etc. These crystals in which there is a single direction known as the optic axis, means they are having only one optic axis in which all the waves are transmitted with one uniform velocity, right? Means they are having the single optic axis. And the biaxial crystals like borax, mica, topaz, etc., they are having the two optic axes, means they are having the two such directions for one particular velocity. So in this case we will get the two optic axis. So this was about the calcite crystal. So this was about this term polarization, and these three topics we have discussed up to this part. Thank you.